So, we have now 10 point groups, we want to combine them with translations, and translations are represented by lattices. So, we want to see how many different kinds of 2D lattices are there with which we can combine these 10 point groups. When we say different kinds of 2D lattices, of course, you have seen that 2D lattices you can select a parallelogram as your unit cell with two basic vectors a and b, an angle between them gamma. And once this is given, once the unit cell is given, you can keep adding more unit cells or more lattice points, and you will get your entire two dimensional lattice points, two dimensional lattice. So, if we think that each a, b and gamma gives me a lattice, there are infinitely many different lattice, because there is no limit of the way in which you can vary a, b and gamma. You can choose any a, any b and any non-zero a. Only requirement on these three quantities is that they should not be 0. If gamma is 0, then you do not have a 2 dimensional, you have a 1 dimensional direction, and if a or b is 0, again you lose the periodicity in that direction. So, once you have 3 non-zero numbers a, b and gamma, you get a lattice, and infinitely many variations are possible. But when we say different kinds, again our kind is based on symmetry. So, the focus is symmetry. So, how many different kinds of symmetries for lattice we can have, or how many different kinds of lattices based on symmetry. So, instead of focusing on symmetry of a finite object, which was the point group, we are now looking at infinite lattice, and we want to look at the symmetry of these lattices themselves. So, let us characterize them on the basis of symmetry. So, I have just drawn some sort of an arbitrary 2D lattice. If a and b are not related and gamma is arbitrary, then what symmetry do I get? Identity will be expected symmetry, but translation is forcing a kind of symmetry. Translation is forcing a kind of symmetry. You can see that if you have a translation b, do not you have a translation minus b, and if you have a translation a, do not you have a translation minus a. What is this telling about the symmetry at the lattice point? So, each lattice point automatically becomes a two-fold, even in the most general case. I am not filling my two-fold axis, because I want to preserve the identity of the lattice point, which will be lost. I am using open two-fold notation here. Of course, you know that if there are two folds combined with the translation A, what does it do? A two-fold with translation A generates another two-fold between the two, it generates a two-fold at A by 2. So, you can see also that you do not have to rotate 180 degree about the lattice point, you can even rotate 180 degree in the midpoint of two lattice points, and everything will come into self coincidence. That is also a two-fold axis, because if I rotate about this two-fold, let us say, then it will take these two lattice points into each other, it will take these two lattice points into each other, it will take these two lattice points into each other, it will take this lattice point into sub lattice point down below. So, the midpoints of the lattice points are also two folds. So, same thing is true for B also. And A plus B is also a translation vector, the diagonal vector. So, in that direction also you will generate a two-fold at half A plus half B, that will be in the center of the unit cell. So, even the most arbitrary two dimensional lattice will be decorated with these two folds, it will have all these two folds. So, this kind of lattice we can say least symmetric lattice. So, we call this the oblique lattice. It is least symmetric, but it still has two folds, and the symbol for this is MP. M comes from the three dimensional counterpart of such lattice, that is monoclinic. So, the international notation tries to somehow bring a connection with 3D when giving the notation. The name wise it is not called monoclinic, name wise it is called oblique lattice to indicate that it is 2D, but notation wise M comes from monoclinic in 3D. Only thing is that if monoclinic primitive lattice in 3D was there, then P will be written with capital. So, that is the distinction one makes. So, P has to be small for 2D. Now, when we are looking at the lattice, we are not forgetting about the point group. So, then we will combine the lattice and the point group to generate the whole symmetry of the pattern, which will be called the plane group. So, first we are doing part work and then we will combine the whole thing. Let us call this lattice 1. Is there any relation between A, B and gamma? There is no relation or no constraint, they can have any value. So, we were trying to classify by symmetry, and the least symmetry, as somebody said, was no symmetry. So, we were trying to create a lattice with point group 1 with no symmetry, but we saw that that is not possible. We by default we have this threefold, sorry, twofold symmetry. So, and we call that oblique lattice. So, the next symmetry, the twofold we will not consider, the next symmetry we can consider 3, 4 and 6 or M and 2 mm and so on. So, let us consider the next symmetry as the mirror plane, because that is an interest, that puts some interesting constraints on my lattice. Because although this has twofold, if A, B and gamma are arbitrary, you are not seeing anywhere any mirror plane. There are no mirror planes in this. So, this oblique lattice is lacking mirror planes. You can't draw any plane in which you can reflect and get the lattice point into self coincidence. So, if I have a lattice with reflection, so let us have a mirror plane. As soon as I have mirror plane, there are certain constraints on the lattice points which will be there. So, for example, if I put a lattice point on my mirror plane, there is no problem. one periodicity direction can be taken as in the direction of the mirror plane itself. So, because each lattice point is then getting reflected into itself as far as the points on the line is there. So, mirror plane is satisfied. The second set of mirror lattice points can be considered in a direction perpendicular to the mirror plane, because I want to preserve this mirror plane, and one I know that if any vector, if any vector A I take, then lattice itself forces minus A, and if a is perpendicular to a mirror, mirror also forces minus A. So, this A and minus A from the lattice and A and minus A by the mirror, it is satisfied if A is perpendicular to the mirror. So, I can have a possible lattice like this, and this lattice will have mirror planes. Of course, all lattice points are equivalent. So, if one set of lattice points were having this horizontal mirror, other lattice points also will have this horizontal mirror. So, you buy one and get several free, because all lattice points have to be identical, and I have said that from my one of set of lattice point mirror is passing. So, all of these are mirror. But then when we considered Freeze group, there again we saw that if a mirror is combined with the translation A perpendicular to the mirror, then mirrors get generated at A by 2 also. And here also you are seeing that although I started with the red mirror, I have green mirrors also, because these are also acting as mirrors. Okay. So, now I have, so you can see I have a beautiful lattice which has one set of mirror planes. But since I put it as perpendicular, it has, does it have another set of mirror planes also? Because two folds were anyway there, any lattice will have the two fold, and two fold we have seen a mirror passing through two fold creates a mirror at 90 degree to it. So, now we are seeing that these two fold and mirrors are also getting generated. So, you have mirrors like this also. Shall I use yet another color? Maybe. And these mirrors also will generate mirror halfway between them. So, if you now see, these were the lattice points. So, you have a very rich system of mirrors and two-fold. All the intersection points are now two-fold, all the lines are mirror. You can call this as your A, you can call this as your B, you can call this gamma. The constraint on gamma now is gamma has to be 90 degree, because we took the second row of lattice points 90 degree to the mirror and one row parallel to the mirror. So, gamma gets constrained to 90 degree, A and B are not constrained and they do not have to be equal either. So, this is a rectangular P lattice, symbol is OP, again O coming from 3D orthorhombic. So, symbol in the symbol the name for the 3D lattice comes, but the 2D lattice has the name as rectangular lattice, but symbol as OP. Is there any other way of preserve the mirror? The constraint which I was putting, that let me have a row of lattice points perpendicular to the mirror. If I don't have that luxury, and if I say that let us have a lattice point which is at an angle to the mirror plane like this, but I want to preserve the mirror plane. So, I have to reflect this lattice point. So, I will get another lattice point there. And if I have two lattice points, two lattice translations, combination of them will also give me a lattice point. So, if I combine these two, I again find that. So, I cannot avoid, if a lattice has a mirror, it has to have several lattice points along the mirror line, whole row of lattice points along the mirror line. So, that first assumption was not that so arbitrary, that I took lattice points along the mirror line. Even if I do not want to take a lattice point along the mirror line, the mirror symmetry as well as the lattice periodicity will generate a set of points along the mirror. That is part of the symmetry game. Similarly, I have negative of this vector also. And then if I combine these two, let us label some of them. So, let us label 1, let us label 1, 2, and then this is minus 2, and 1 and minus 2 again can combine to give you a lattice point there. And what is the orientation of that lattice translation? If you combine 1 and 2 is reflection of 1. So, this theta has to be equal to this theta, which will be equal to this theta. So, if you combine 1 and 2, 1 and minus 2, the vector which you are getting, what are you getting? Maybe instead of 1 or minus 2, I should label them as A, B or something. Suppose this is A, this is B, this is minus A. So, this vector is minus A plus B. So, I am asking what is the orientation of minus A plus B with respect to the mirror line? Minus A plus B will be perpendicular to the mirror line. So, you can see that other assumption also in the first case, to have a set of lattice points perpendicular to the mirror, was not really arbitrary. Even if you start with an arbitrary lattice point which is not inclined, you will generate in the end a set of lattice point perpendicular to the mirror and a set of lattice point parallel to the mirror. But now, if you look at this lattice, the lattice which you have created, it's slightly different. Yeah, it's not primitive. If you think in terms of rectangle, it is having centers also of the rectangle. This way of creating gave me a primitive, and that is why that P was there, primitive. But this way of creating it again gave me parallel and perpendicular rows of lattice point, but it is giving me this middle lattice points also. And since all lattice points are equivalent, again you will have mirror planes passing through all these lattice points. And similarly you will have mirror planes passing through this perpendicular set also. So now you can take this as your A, this as your B, and call this centered rectangular lattice. No, not necessary. A and B are arbitrary. It's not a square, it's a rectangle.
So their angle will be equal, this theta.
Theta angle is equal because A is reflection of B. So reflection should not change. A is reflection of B in, sorry, no, I am using two A's and B. So let me use prime on these. Let us say A prime, B prime. Okay. So A prime is reflection of B prime. So reflection will make the angle equal. Then minus A prime is just opposite of A prime.
So A prime and B prime will have length also, same length.
Sorry?
A prime and B prime are equal.
Yeah, A prime and B prime are equal, because sorry, yeah. So that is why it is important to keep this notation different. A and B are not related. A and B are not related because B is finally A prime plus B prime, and A is finally B prime minus A prime, or A prime minus B prime if I am drawing the downwards. Oh. Yeah. So in the primed symbols they are equal, because A prime is a reflection of B prime. So reflection does not change length, so they will be equal in length. But when you combine them, since one of them is A plus B and another is A minus B, then this new A and B, which are the sides of the rectangle, they are not equal. So they are not constrained, unless and until A and B themselves had some relation which will make this equal. So that will be accidental or coincidental. So this we will call orthorhombic C in terms of symbol, or centered rectangular lattice. Okay. So we generated 3 lattices. One was oblique, one is a primitive rectangle, and one is centered rectangle. There are actually 5 lattices. So, 2 more lattices we have to create, which we will do in the next class. Yeah, lattice should have.
Second lattice should have more symmetry than third.
Yeah, it is having. So, we have not looked at it carefully. Okay, let me draw that. So, just the unit cell for quickness and simplicity. So, you have mirror here, you have mirror here and you have mirror here, you have mirror here, you have mirror here, and you have mirror here, and these are the lattice points. Thank you for raising that, because I was missing that point when I said that this is a new lattice. If it has the same symmetry, then it is the same lattice, even if it is a centering point. So, centering point should not create a new lattice, it is the symmetry which should create the new lattice. So, why this we are considering with the center as a new lattice, that now if you see, so these lines are glide lines, because you can see that you can translate this mirror, translate this lattice point by b by 2 and then reflect in this dashed line. So, you will reach this lattice point, the central lattice point. Similarly, there is a glide here and there is glide this way also. And intersection of glides are also mirror two folds, just like intersection of mirrors are twofold, intersection of glides are also twofold. So, now if you compare, you will see that this is really having much more symmetry elements So, OC has more symmetry than OP, which was having only the mirror, has two sets of perpendicular mirror and two-fold. It has two sets of perpendicular mirror and two-fold, also two sets of or one set of perpendicular glides, also with intersection as two-fold, new two folds coming. And that is coming because we have these centering lattice points. Absence of centering lattice point removes the glide and the green two folds. But if the centering lattice point is there, then you have the glides and the green two folds also. Okay. So, in terms of symmetry also, this centered lattice, centered rectangular lattice is a different lattice from the non centered one. So, thank you very much.